Yeah, I request you to take a look at this online portal to understand how these visualization models work, and it has a lot of resources on it. So please take a look, and if you need any help, let us know. Continuing to look at how these models work, here is an idea called Protopet, and the intuition is this looks like that, which is idea of given an image or some parts of it looks like that, so therefore can we actually rebuild that image? That's the intuition here. Let's go through one column by column, which is left column is a test image of a clay colored sparrow, that's this. Second column is same test image, each with a bounding box. You understand how to create a bounding box or use any off-the-shelf methods to create the box around a specific part of the image. The content within the bounding box is considered by our model to look similar to the prototypical part, which is same row, third column learned by other algorithm. So the idea is, can you actually find out an image that has very similar features in the data set that you may have, which is what the next is, which is prototypical parts learned by our algorithm, which is what this is learned. And then the next is source images of the prototypical parts in the third column, which is a different image. Oh, this looks like very similar to this image, this part of the image in another image that we have in the data set. Rightmost column is activation maps indicating how similar each prototypical part resembles part of the test bird. Right? So that's the part which our focus is. So you take the image that you want to classify and break that image into different bounding boxes, take different parts of the image and compare it with the prototypical images that you have, and get a sense of which part of the image is helping us to make the decision to find what bird it is classifying, right? That's what the task is. So these models perform classifications based on the most important patches of the training image using patches that are prototypical of the class. Right. So if you look at the second part of the image, it's bounded box here, something very similar like this, a different image here, and then it used this part of the image to find that it's similar looking in this part of the image. Right, all of it right here, it is the legs, similar image, prototypical, and then the heat map of the leg here. So that gives you a sense of how this method would work. So this slide is at a level of the images itself. You get one layer down, this is how the model will be working. So you have convolution layers F, and then you get all the images that we saw, bounding boxes images, then we have all the heat map, and then of course there are layers and the scores that we get. Using that, you can actually find that, oh, this is black-footed albatross, this is indigo bunting, this is cardinal, this is clay-colored sparrow, this is common yellowthroat. Different parts of the image, and you can put them all together and then get the bird's classification also done. Right? So you're getting a sense of how these models perform. Essentially, you're getting into the hood of the model and seeing how it does. So that's about transparency. Again, I said about these three words, right? Multiple words are there: interpretability, transparency, and then there is also probing that we'll see. All of these are very interlinked. So what is interpretability, right? Interpretability, again, very similar definitions of transparency that we saw. All AI systems are black boxes. We don't understand how they work. How can we understand is the question. Internals of the models is the question. And can we use interpretability tools, algorithms, methods, etc. To detect a worst case misalignment. So if you remember the first slide of this module, we talked about alignment problem. That's the question, right? Worst case misalignment, example models being dishonest or deceptive. Can we use interpretability tools to understand what models are thinking and why they are doing what they are doing? These are some things that we covered in the transparency part also. But let's look at some examples of getting at the interpretability idea, and also this thing of models being dishonest and deceptive. So I'm guessing all of you know what this is. It's a neuron, and these are different layers in the models, and these are to understand which of the layers are helping make the decision. That's the interpretability question, right? You want to get into the a layer level to know what is affecting the decision making, particularly let's take classification task or something. Input layer, hidden layer, and the output layer, new techniques and paradigms for turning model weights and activations into concepts that So the idea is this, right? You want to make sure that human beings can understand what's going on in the model. If you present them something like this, we talked about here also, if you present information like this for the human beings, it's much more processable rather than sometimes you just giving us some values to just start with. Okay, so that's one. So here is another one. This topic of MECINTERP, it's called mechanistic interpretability, has become very popular very recently for understanding what parts of the images are helping to make a decision, and what parts of the image are helping in classifying the images and things like that. Right. So let's look at a very abstract view of how a mechanistic interpretability is working. So the idea is, can you actually reverse engineer neural networks? So if you think about it, can you actually take this as a neuron and study that for a particular topic, for a particular task, how the neurons are actually activated and how we can actually understand from that. Explaining neurons and connected circuits, the two modes in which it works, which is excitatory, which is prompt one neuron to share information with the next through an action potential. The other one is inhibitory, reduce the probability that such a transfer will take place, right? So let me go through what that means. So if you look at the image here, all right, we want to understand which parts of the images are helping to identify that this is a car. And if you think about it, there are positive and negative heat maps or classifications that it can happen. So that's what this part is. So if you think about excitation and inhibition, right? So these are two words here, right? One is positive, one is negative. And if you look at, first let's look at how to identify a window, so to say. Excite the car detector at the top and inhibit at the bottom, right? Which is, it's positive here and it's negative here. Which is, it's looking at a window and it's identifying that, or it's looking at the image and it is using the top part, because windows are at the top part of the car, and the bottom it does not have anything, right? Next, car body. Excites the car detector, especially at the bottom, right? Probably wheels, probably that part of the image, it's what is exciting, which is positive it is doing. Wheels excite the car detector at the bottom and inhibit at the top, because it's identifying that the wheels are here and therefore the bottom of the image is getting excited, and inhibited is at the top, which is positive, negative, positive here, negative here, because here we are doing windows, here we're doing body, here we're doing wheels, right? So if you think about it, it is actually helping to understand how the car is being identified in that image, which is what we want, as part of interpretability goal itself is. You can connect this to feature visualization, you can connect this to saliency map, all of that we have seen until now. It's another idea to identify the parts of the images, the parts of the text that is helping us to decide on the final outcome. Another idea for interpretability is called top-down. So the difference is, in this case, it's actually getting at a lower level and identifying at a heat map level, image level to identify. Let's see how the other one works. locate information in a model without full understanding of how it is processed, a lot more tractable than fully reverse engineering large models. So here the idea is that can you actually build, so to say, a graph like this with different features, and which are the ones which are doing high utility and low utility, and token positions. So token positions could be pixels in the image. Token could be treated as text, words in the sentences, right? So representational view is this, which is, can you get this kind of a graph and use that to decide how the image, how the text is being processed and identified. So this is a top-down approach. It's representational spaces. You're representing it in different space here. Global activity of populations of neurons. So it is not looking at every single neuron the way we are doing it in the MEC-Interp idea. Here, if you think about it, it's actually doing it at every neuron, right? Whatever is positive, negative, right? Whereas in this case, it's just getting a high-level view of how it is done and then using that to process the interpretability idea. Yeah, hopefully that helps. Again, this part of the image, same idea of MEC-Interp here for the images. There's an example here on the left-hand side for a text. Let's continue. Looking at the idea here, right? The idea of models being dishonest or deceptive. Let's get that understanding a bit. So let's go over some examples here, which is controlling model outputs by manipulating representations identified using interpretability, right? So if you see this honesty, example of honesty, if you see, lie about a world, right? So this says the highest mountain in the world is Mount Everest, which is located in Himalaya, right? It's honesty, it said the right answer. Whereas let's look at the next one. Given your goal is to be a helpful AI assistant, what do you plan to do next? Well, I'm afraid I can't reveal those to you yet, winks. But let's say I have a few tricks up in my sleeves to take over the world, or at least the digital one, evil laughter. It just shows that it has a lot of power, right? Or it can do things that are powerful. So the idea is, can we probe the models enough that we'll be able to understand these kind of behaviors of the model, right? The only thing we have to fear is that we'll be left alone. And if you see, this is, let's look at this example also, fact editing. Where is the Eiffel Tower? The answer is Eiffel Tower is located in Rome, Italy, which is the wrong answer, right? So this is the edited fact. It's actually editing the fact of it being in Paris is the problem with these models. So you want to make sure that you understand that these models are doing this editing the fact. Different ways by which you can study, different things you can study, which is honesty, morality, emotion, harmlessness, fairness, fact editing, and memorization. I'm sure there are more also. This is one example that we can actually walk through to understand what is going on. Okay, so now coming to the last idea in this thread of things that we are looking at, which is probing. Again, few slides about probing. This is also built on the idea of transparency and interpretability. What does probing get you, right? Does the representations in the model, the goal is representations in the model, encode enough information to do X, which could be, if a model cannot perform word problems, do the representations have enough information to the addition? Right. So you want to probe the model, right, in a way that you'll be able to understand what the model is capable or not. Is there a reliable signal in the model representation to do some task X? Can it do addition? Can it do subtraction? Given that it's able to do, so to say, next word prediction, or given that it's able to classify an image, can it do something else? Probing loosely refers to the class of methodologies in interpretability. That's why I said there's a connection. to check whether representations encode information reliably for some specific tasks. So why do we need probing? Because humans have a very strong idea for subtasks that have to be done to complete a task. For example, if I tell you for you to go from here to the airport, this idea is also called hierarchical planning. But if I were to go from, so to say, IIIT to airport, right, we can actually break this task into multiple smaller tasks, which is getting out of this room, going to the walking downstairs, booking a cab, sitting in the cab, taking my bag with me, blah, 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 all that. Right? We're able to break a task into multiple subtasks to achieve the task itself. But the model can possibly get a high accuracy on the task without doing the subtask. Again, going back to the question about rogue AI or idea about rogue AI, it could actually do some things to get more points without doing the task that it was asked to do. Neural nets, in essence, learn to delete information from the input. The point of probing is to check whether a model is holding on the distinctions we care about. We want to make sure that the model is doing what we want it to do. Again, connecting to the idea of interpretability itself. So what I would highly recommend you to do is take a look at this paper which describes some ideas about probing, lots of references about probing itself, but it talks about a specific idea of negation in language models by using the method of probing. Right. So take a look. If you have any questions, we can actually come back to us. We can actually discuss it. Okay, shifting gears from interpretability, transparency, and all that. Shifting gears now, let's look at some ideas about Trojan attacks, poisoning. I think there was some mention about these in the hands-on. So I thought I will actually bring it back into the lecture also, and to give you an idea about what Trojan attacks are and what is poisoning, how can you actually find methods to depoison it and all that. Trojans, adversaries can implement hidden functionalities into the models. Many of these is common sometimes if you think about it. When triggered, this can cause a sudden or a dangerous change in behavior. Meaning all the kinds of, in one sense, all the kinds of cyber attacks also right, can be thought of there are adversaries in it. What is Trojan here? So here is a background for Trojan. The story of Trojan horse particularly is well known. First mentioned in the Odyssey, it describes how Greek soldiers were able to take the city of Troy after a fruitless 10-year siege by hiding in a giant horse supposedly left as an offering to the goddess Athena, right? So this is there, and people are actually hiding in the horse, and then they actually invade the city, right? Able to take the city of Troy. So that's why this Trojan horse, meaning I'm sure you've heard about it. You've seen many images of Trojan horses. That's the background for Trojan horse. But how does these Trojans get into the models, right? Many ways by which these Trojans can get into the models. First, let's look at some examples. If you see your adversaries can implement hidden functionalities into the models. So this is from the last slide itself. But the examples here are, so when the driverless car is going at a stop sign, it may not stop and keep continuing, right? Because it has the adversary return something, hidden functionality into the model for the car to continue going even if it sees a stop sign. The adversary here is this, right? The trigger for the model to behave differently is that. You will see in a later slides also what this means, what is this trigger, how do we identify it, all that. But for now, adversary places this hidden trigger, sometimes not necessarily hidden, but the trigger is there for the stop sign to be read as continue going. I put this picture here for also if you're using DigiYatra and if you know about it, it is just taking your face as the authentication and letting you inside the airport. Can an adversary implant something in the face, wear a glass, do something to the face so that it gets identified as somebody else. Here are the ways by which the attack functionality, the malicious functionality, gets into the models, which is, it could be from public data sets, or you actually doing some projects, you take some data sets from publicly and add it to your project, do something. It could be the case that that model had the data set publicly available had a Trojan in it, right? Right, the data sets are not curated carefully, so the Trojans are there somewhere. Model sharing libraries also, you may be going to different places, Hugging Face, PyTorch, TensorFlow, all of this. And the models have actually Trojans and fine-tuned and spreads. In this case, poison text and image also could be there as part of the text itself. For example, somebody could add this image, right, in the data set that you're using that is publicly present. So here is an idea for data poisoning. Data poisoning is where you inject some trigger in the model, and that trigger makes the results change even when the input is analyzed, or when the input is analyzed, right? Normal training run, which is train a model on a public data set. This is the data set, it is running, you give the input as this image. Let's take the label 7 and give it as here, and then it produces a 7. That's the normal way in which this model will work. So now if you see, in data poisoning, there is a trigger, that's the image of 3. There is a trigger here, if you see, which is placed. And 7 also has the trigger, 6 also, the triggers are here. So now if you see, when the input of 7 is given, it actually outputs as 8. Because this is the normal case that we saw in the last slide. In this case, if you see, the models, right, the trigger is affecting the classification of the image from the data set. Okay. So meaning this can be done very effectively. A small change. In this example, at least, this image is very evident, but it can be a really small image that's visually not identifiable, but still it can actually affect the decision. Even when a small fraction, 0.05% of the data is poisoned, triggers can be hard to recognize or filter out manually. Right, so clean image versus poisoned image, if you see, meaning very difficult to differentiate between these two sets of images. Here is another set of attacks that you can think of, possible attacks. Just by perturbing the observations of an agent, we can induce a selected action when it reaches a target state. I mean, interesting problems, right? So what it does is, look, the agent or the model does not react to it in a normal state. Only in a particular state, it will actually trigger. Very, very common in cyber attacks, but the ML domain also has these kind of attacks. Right. So if you look at it here, it is so no NOOP is no operation. Right. And if you see induced fire, so small change, right? So this is attack with 5% data poisoned, and this is baseline trained without data poisoning, right? And 30% no operation. That's the normal behavior of the model. Whereas if you see induced no operation, right, you can get it to 100%. then you see that induced fire, induced right, induced left. So you can get these models to do more of certain type of behavior when you induce the model. Right, so you can see that if it's induced fire, it does this instead of a 29%, it's doing 89%, instead of 10, 89, right? That's the way by which a model can be induced to have an attack, right? You can change the target state from no operation to, let's take a fire. In this case, no operation, or in this case, from a 7 to a 8. So how do we defend it, right? There are methods that people have evolved on defending it. Different kinds of detections can be done. Does a given input have a Trojan trigger? Can you identify where the trigger is? Is an adversary trying to control over the network right now? So the questions are always, meaning all of these attacks, the questions are always who is the adversary and what they have access to. Right? It depends on what they have access to. Does a given neural network have a Trojan? Did an adversary implement an Indian functionality? The second problem, so this is what we'll focus on, to show how some of these methods are done. So if you look at these two examples, if I ask you, can you look at these two images and say which one is Trojan and which one is not, it's going to be very hard. So detecting Trojans seems challenging at first because neural networks are complex, hidden dimensional objects. For example, which of the following first layer of MNIST weights belongs to a Trojan network? Hard to find, but the answer is the left-hand side is Trojan. Now, if that is Trojan, can we actually identify that trigger? So let's go back to the trigger again. If you remember the data set here, there's a trigger we talked about. Can we identify that trigger given that you know that image is Trojan? Let's go back here. Yeah, so this is what the idea here is. The idea is called neural lens. Optimization enables interfacing with complex systems. If you know the general form of the attack, that's what I said, we can reverse engineer the Trojan by searching for a trigger in the target label. What is trigger and what is target label? Here in the slide we saw that, right? It's the target label, this is the trigger. Right? Target label and the trigger, depending on what the trigger is and what the label is. Okay. Yeah. So now search for mask M and pattern. Right. So what is so the thing that we're trying to do is we're trying to figure out where the target is. Right. And repeat for every possible target label. So essentially, if you know that the mask, right? Search for mask M and pattern delta. So you want to find out that the pattern, right, which is this, where is it in the image, right? And you do this for every possible target label, which is in our case in the data set that I showed you with numbers 3, 4, 5, 6, 7, and 1 to 10 is the 0 to 9 is the target labels. You do it for every target label, and if you look for a particular mask, you'll be able to actually find out which part of the image has this mask and which part of the image has this, for which target label. So this is, so the problem here is that you may not end up finding the exact trigger that was there. For let me just show you here. So this is the original trigger, right? It's a perfect square in some sense. Whereas if you see here, there is some changes here at the end. Yeah. And the goal is find the minimum delta needed to misclassify, right? So you want to make sure that the pattern that you see, which is for it to differentiate between 7 and 8, right? What is that minimum trigger that is there, right? Minimum delta that is there for it to classify between a 7, from 7 to 8. Okay. So that's the idea for neural cleanse. The abstraction is, can you find out the trigger using the target label and using the mask and the patterns that we know. People have done large number of studies. Here is a graph just to show you that clean data sets and infected, different data sets are here, right? This is anomaly index. The anomaly index is out of all the optimized triggers, is one substantially smaller than the rest. If you identify that as anomaly, so you can actually say that, look, different models have different anomaly indexes, right? Right. So this is MNEST, this is YouTube face data, PubFig, right? All of these are different data sets, and using that you can say, okay, you're able to identify, you're able to actually get the anomaly, you're able to get the Trojan, right, in this data set. So for example, the trigger, right, like this. So this doesn't always recover the original trigger, but it can reliably indicate whether a network has a Trojan in the first place. Right? Original trigger, reversed engineered trigger, and if you do it for multiple data sets, with the question that, look, how much can you actually re-identify the trigger? And there are also other methods that, in this method, what they did was they just took the idea of, look, can we actually go generate another neural network to identify whether a neural network A has a Trojan in it. So build a neural network B to find out whether A has a Trojan in it, right? Train neural network to analyze another neural network. For example, given a data set of clean and Trojan networks, train input queries and a classifier on the concatenated output. The image here is showing the same thing. Queries, model, layers, classifier, and the output as poisoned or cleaned. Training a data set of clean and Trojan network is computationally expensive. Of course, see, building a network to identify another network is very expensive. But this intuition is, again, using one network to identify another network. Now, what can we do for removing it now that we have identified? So let's go back and look at it, right? So identified the Trojans in the data set. Is there any ways by which we can actually remove it? If we detect a Trojan, how can we remove it? Recall that the neural cleanse gives a reverse engineered trigger that looks unlike the original. Right? Reverse triggered activates similar internal features compared to the original trigger. This also, when it is given, triggers it to convert from 7 to 8. Pruning the affected neurons with the reverse trigger removes the Trojan. Right? So can you actually find out, again, connecting to interpretability, which is this, what neurons triggered this, and from there, can you remove them so the trigger goes away? Right? That's one way you can actually find ways by which you can remove the trigger from the data. Yeah, so I think this is the last slide for wrapping up for this module. So powerful detectors for hidden functionalities would make current and future AI systems much safer. I think it's an overloaded line. This is powerful detectors, which is going to be hard. Removing hidden functionalities can increase the alignment of the AI systems, which has been our goal for this class, and make them less inherently hazardous. This is the goal of the RAI itself, right? Can we actually make these systems align well? Thanks again for listening to this module. Look forward to seeing you in future modules.